In this video, we're going to talk about using Simulink to simulate your state space models. You've done this already. In Lab 1, you've simulated your state space models using ODE45, an inbuilt MATLAB integration routine. And the way that worked was you built a function which represented your model, and then you wrote some computer code, some MATLAB code, which told MATLAB to go away and use that ODE solver to integrate your function over time. We're going to do a very similar thing in this case. We're going to represent our model as a block diagram within Simulink, and then graphically, using Simulink, we're going to tell MATLAB to go away and use an ODE solver to solve our system, to integrate our system over time. To get started, we need to open up Simulink, and you do that from the MATLAB command window at the top here. You click the Simulink button, and if you're on a Mac computer, it opens up straight away. If you're on a Windows computer, your mileage may vary. And then you click a new blank model. Your interface might look slightly different to this if you're working with an older version of Simulink. I've got 2019A here, and that was at the time this video has been produced. I can encourage you to always work with the latest version of MATLAB and Simulink. It's just generally going to make your life easier in terms of compatibility with the assignments we put out, in terms of the functions and blocks that are going to be available to you. It's just generally going to make life easier, and if you download it at the uni, it'll download very quickly and you should have no troubles. Alright, we're presented now with a blank Simulink window, and this is where you draw in Simulink your block diagrams. In this example, we're going to do a block diagram of the mass spring damper system, which I'll put up now. That system we've modeled in class before, back in week 1, and that system had the following state space model and block diagram, which I'll put up on the screen and leave there while we work through these examples. So, this model we're looking at has 2 integrator blocks, 3 gain blocks, and a sum block, as well as a constant block which we're going to use to represent the input. Of course, the input could be some other time-varying function, but let's assume that the force being applied to the mass is a constant in this case. Alright, to place new blocks in Simulink, you've got 2 options, at least in the later versions. You can click anywhere on the screen, begin typing the name of a block. So for example, I want an integrator, INTEG, and I'll get a list of blocks that have those words or those letters in their name. I can choose integrator, which is the first one that's offered, and it drops that block in for me. Simulink, if a block requires extra information, will prompt you for that information when you place it. So for example, initial conditions are something you must specify to run your simulation. The system needs to know where to start. And initial conditions in Simulink are specified within integrator blocks. So I've placed down an integrator block, Simulink's identified that it needs that information to proceed, and it's asking me for the initial condition for that state now. I don't have to provide it now, I can just ignore Simulink, click off it, and go about my life. But if I try to run this simulation, it's going to throw an error. So I can always come back later, open up that block by double clicking it, and inside of the block parameters, I'll be able to modify that initial condition just here. I have a whole bunch of other options that I can change as well. While you're getting started, I recommend you don't touch any of those. The default options are perfectly fine for what we want to do, and perhaps later on when you get a bit more comfortable and competent with Simulink, you might consider messing with some of those. I like to put in all of my settings at the end after I've built the block diagram, so I'm going to leave that for now and come back to it and begin to drop in the other blocks. The other way that I can add blocks to Simulink is via the browser window or the library window, which is good if you don't know exactly what it is you're looking for, if you don't know the name of the block that you want. So you click the browser window up here, and Simulink immediately goes into the commonly used blocks window. Sometimes you might find it goes into this top level folder window, but from here you can access any of the kind of categories of block that you were looking for. Commonly used blocks is where you're going to find most of the things you're going to need most of the time. Things like constants, gains, integrators, products, sums. So in this case, looking at the model that we're dealing with, I'm going to need 2 integrators, so I'll need 1 more. So I'll grab that one and drop it in. I'm also going to need 3 gains and a sum. I usually find it's quicker and easier just to type the name of the blocks I'm looking for. So I want gain, and I want 2 other gains. But if I look at the model, the gains I've got drawn there are actually pointing the opposite way, or at least 2 of them are. You can do that by right-clicking a block in Simulink, choosing rotate and flip, and flipping the block. And once you've done that, rather than need to place another gain and go through that process again, I can just copy and paste Control C or Command C if you're on a Mac, and Control V or Command V if you're on a Mac, to paste. So I can begin to arrange these things the same way that they appear on my block diagram that I've drawn by hand. Put that guy there. This one was living somewhere here, as was this one. And I still need a sum block and a constant block. So let's see, up here somewhere, I'll just click first and then type sum. And this block requires some extra information. It was asking for a list of signs. That list of signs is just telling it how many inputs you want and whether you want those inputs to be positive or negative. Remember, when you're drawing a block diagram, you have the option of specifying whether you want to include the negative signs in the gains that apply to the signals before they get there, or whether you want the negative signs to be applied at the sum block. I prefer the former. I like to put my negative signs in the gains and keep the sum blocks only taking positive quantities. Makes it easier, I feel, for me to track what the value of those signals are. Finally, I need a constant block to represent the input. And what I should do is modify this sum block so it takes 3 inputs. So instead of having 2 positives, I'm going to have 3 positives. And I'm just going to rotate this block clockwise so it points roughly in the right direction. All right, I've now got all the ingredients for a successful Simulink model. And I didn't have to worry too much about layout because I'd already done that work in building the block diagram by hand, which is extremely good practice and something you should aim to do. You should always aim to hand draw your block diagram before you start to put it into Simulink. First of all, it will point out any errors you have in your modeling. If you draw the block diagram and you notice that the signals the information isn't flowing the way you were expecting, it's something that's quite easy to fix on paper. Whereas deleting all of your signals in Simulink, your interconnections in Simulink can be a pain sometimes. Also, it helps you lay out your diagram in a way that's going to be convenient for when you put it into Simulink. Again, because once you've connected the signals in Simulink, you want to move blocks around, those things can get a bit gross. Okay, the time has now come to start putting information into my blocks and making the interconnections. I like to connect everything first and then fill out the blocks with the right information. You can see that right now my input is 1 and all of my gains are 1, and I haven't set initial conditions for my states. So I'm going to connect the dots and then I'm going to fill in all of those blocks. So let's see, the input feeds into here. That sum feeds into the back of this integrator. That integrator feeds into the back of this gain, which feeds into this integrator, which feeds into the bottom gain, which feeds into the sum block. And then this gain here also feeds into the sum block, and it gets its signal from just after this gain. You'll notice if you try to grab this one here, you're not able to kind of feed that into the gain block. It just tries to put a kink in that signal line. So what you do is you grab the output first and you drag it back to where you'd like to branch off, and that little dot indicates that there's a bifurcation point there. It's not 2 lines crossing over the top of each other, it's actually that signal splitting and going in 2 directions. Okay, now it's come time for me to start to put in my settings. So this gain here was 1 on M, this gain here needs to be minus B, and this gain here needs to be minus 1 on C. I should mention, you can actually run all of your simulations entirely within Simulink. You can set up your initial conditions, you can put in your parameters, and you can look at the results entirely within Simulink without having to use MATLAB code at all. This can be good if you're doing a quick and dirty simulation, you just need to know the answers. But it isn't good if you want to do a parameter study, for example. If you want to change something like the mass of a mass spring damper or the stiffness or compliance of the spring. It's not good if you want to do that because every time you'll need to open up these blocks and change the parameters. So what we'll do is we'll start first by running everything within Simulink, and then we'll talk about how you can write some code to drive this model. So let's see. Let's make the force, we'll call it 10 newtons. Note that I'm not putting units in this at all, right? MATLAB doesn't know what units I'm operating in. It's my responsibility to keep track of the units and interpret the results correctly. So I don't have to put this in as newtons. That 10 could be, it could be pound force, for example, right? It could be pound force. Obviously, you wouldn't do that. I recommend you work in SI units all of the time, and then your life will be good. Okay, down here in this game block, it's looking for minus B. Let's just give that a value of -1. So we're saying B is equal to 1. And stiffness of the spring needs to go here, -1 on C. So we'll go minus, let's make it quite stiff. Let's go -5. We're nearly done. Up here, we have 1 on M. So I'm going to make that, let's go 1 on, let's make the mass 7 kilos. Okay, and you can see it's actually chucked those numbers in there for me. If you have very long numbers, 5,000 for example, let's do that, -5,000. If you have very long numbers and it can't fit the number in there anymore, MATLAB and Simulink are going to replace the number in there with a K. So when you're looking at it, all you'll see is a K, but if you double click it, you'll see that the value in there is still the number you tried to put in. You can also make your game block bigger and you'll be able to see the actual number. That was supposed to be -5. Let's not make our spring that stiff, or we're going to send our mass spring damper into the next century. All right, I have one more thing that I need to input before I can run this simulation, and that is the initial conditions. So looking back at my block diagram, this state over here was Z1, and this state over here was Z2. And it can be quite tricky to keep track of these things in a Simulink model, so it's not a bad idea to double click a signal line and add a label to it. That was Z1 and that was Z2. Doing so doesn't change the results. It doesn't modify the model at all. It won't change the way it simulates, and it won't change names of variables. It's just giving you a label on that signal line so that you can interpret what it means. By the same token, this state was momentum, and it goes into 1 on mass, which means that this line here is velocity. So if you really wanted to, you could add another label to this and call it V for velocity, and that would also be perfectly fine. The more information you put in your Simulink models, usually the easier it is for you to debug what's going on if there's some sort of problem. I'm not going to do that though. So I need to put in my initial conditions. This one here was Z1, which was position, and this one here was Z2, which was momentum. Let's say I start at a position of 0, so I'll leave that initial condition the way it is. And let's say I start with a momentum. Let's say I start with a momentum of, let's say 1 kilogram meter per second. So it's going to be traveling forward with some velocity, right? The mass here is 7 kilos, so I'm traveling with a velocity of like 1/7 of a meter per second. Once I've done all of this, I can change the amount of time I would like to simulate for up here in this little box. At the moment it's set to simulate for 10 seconds, which should be fine. We'll run it and we'll see if we've seen all the transient effects by then. If we haven't, we'll simulate for longer. Finally, we need to save our model. I'm just going to say, yep, that's fine. Let's call it my first model. Save. It saves with a .slx extension, a Simulink model extension. Previously, in very older versions of Simulink, it would save with the .mdl. So if you have an older version of Simulink, you might find that it's trying to save with .mdls. Sometimes these things aren't backward compatible. So if I create a .slx with R2019A, unless I specifically set it to be backward compatible, you might find you have trouble opening it with, say, Simulink 2014 or something. Again, a good reason to go and download the latest copy of MATLAB and Simulink, which you can get for free as a student. You can download using the Uni's super fast internet. Okay, now that I've saved it, I've set my initial conditions, I've filled out every block, I should be able to run my simulation using this green button. Let's run it and see if it throws any errors. You can see down there in the bottom left, it's giving me information. Eventually, it's got to the state of saying, okay, yep, I'm finished running. What would you like to do now? So just because I've run the simulation doesn't mean that I've asked Simulink to display any results or give me any feedback. So all it said is, yes, it's possible now to run this. And you can see that down the bottom, it's using the automatic choice of what kind of solver it should be using to integrate this system, and it's chosen ODE 45. So if I'd like to interpret the results, I have a couple of options. I can either export them to MATLAB and then plot them as we have in the past, and we'll talk about how to do that in the future. Or I can view and analyze these results entirely within Simulink using what's known as a scope block. A scope block is just a way that we can view information. So if I want to plot the two states as a function of time, I can say I'd like two inputs to this scope, and I can drag those inputs to the two states. So let's see, I want to scope this signal down here, which is Z2, and this signal just here, which is Z1. A scope can be very useful for analyzing your results and determining whether your model is giving you sensible outputs without having to go through the pain of writing MATLAB code first. So let's rerun our model now with that scope block attached. And it's going to go through running and ready. Now I can open up the scope block and see the simulation results. And there we go. I've got two signals going into this scope block, and this is what they look like. You can see we obviously haven't simulated for long enough. While this signal seems to be decaying, we certainly haven't reached steady state. So this would suggest that what we need to do is simulate for a longer time. So we can do that. We'll go up here, instead of simulating for 10 seconds, let's simulate for 100 seconds. We'll run it again. That happened pretty quick, again, probably because we're working on a Mac. And now we can start to see the results. So whatever this one was, whatever this signal was here, as oscillating, and eventually reaches steady state around the 80-90 second mark, and so does this other one. Okay, let's talk about how we can use MATLAB to drive this, because Simulink is not the be-all and end-all, and often you may want to run this simulation for more than one parameter. Already this is getting hard to track, right? If I said I want to change the mass and observe how that changes the results, well, I need to first of all know where the mass was, which means constantly referring back to my original block diagram, and eventually I'd find out it's living in here. And then I would need to manually open up the settings for that block, change it, let's say from 7 kilos to 6 kilos, apply it, click OK, click Run, then reopen the scope, and then look at the change in results. And that information isn't stored anywhere either. So I need to maybe take screenshots of these things and continue to compare them to each other, which is also not really an efficient use of our time. So what we're going to do is we're going to write some MATLAB code which will drive this Simulink model. To begin with, we can get rid of this scope block because we're no longer going to be analyzing our results within Simulink. Instead, what we'd like to do is send our results to the MATLAB workspace when we're done. So I'm going to use a block called toWorkspace, which sends information to the MATLAB workspace. You get to choose what variable you'd like to call it. I think a sensible choice for the variable Z1 is going to be Z1. And I'm just going to grab that there. And these things work pretty much the same way the scope blocks work, in that you just connect them up to the signal you'd like to export, and then they will get exported to the workspace. I also want the variable Z2. I'm going to click and drag that there, and I can change the name of that variable inside the block as well. Click apply. You need to be careful. MATLAB's default for exporting these variables is not as an array, not as a vector as you might be used to, it's as a time series. Generally, you're going to want to work with vectors, so what you need to do whenever you use a toWorkspace block, unless it's already been given to you, in which case I'll have done it for you, is open up the save format and change that to array. Same for Z2, open up the save format, change that to an array. And now when they get exported to MATLAB, they're going to be exported as vectors that we can operate on. Simulink has some things that will export to the workspace by default. If you open up the simulation settings just here, you also have control over the data import and export. You can choose what variables it's going to send to the workspace automatically. So for example, you can force it to automatically send the states, the outputs of the integrators to the workspace. The trouble with doing that is it doesn't clearly identify which one is Z1 and which one is Z2. You kind of have to interpret that yourself. So I don't like to do that. I also don't like to have anything else sent from Simulink to the workspace. I like to manually control that myself using toWorkspace blocks. Because I've done that, in addition to exporting the variables I'm looking at, Z1 and Z2, I'm going to need to export the simulation time. And we do that using the clock block. This clock block, it just generates the simulation time. There's no need to mess with any of the settings. That time will correspond to the same things, the same increments that Z1 and Z2 are using. just need a 2 workspace block here. I'll call that variable t for time, and I'll connect that dot. Make sure that t is stored as an array, same as Z1 and Z2. And now when I run my simulation, t, Z1, and Z2 should be exported from my simulation to the MATLAB workspace. So let's run the simulation again. And now that's done, let's go have a look at what's living in the MATLAB workspace. You'll see that there is now a structure that's been saved to the MATLAB workspace called out. If I look at what's inside of out, you'll see that it says it's a Simulink simulation output, and it has 3 elements inside of it: T, Z1, and Z2. These are the things that we decided we were going to dedicate 2 workspace blocks for. To access any of these vectors, because it's a structure, we use the MATLAB structure syntax, which is out.variable name. So out.t is going to give us the vector t. Out.z1 will give us the vector z1. Out.z2 will give us the vector z2. And we can, for example, type plot out.t against out.z1. And if we do that, MATLAB generates a figure window with the results from the simulation. So you could imagine if you wanted to run some sort of parameter study, you could change the mass, save the results to the workspace, maybe save it to a mat file, maybe store it in a matrix, change the mass and do it again. And you could end up with all of this information saved, and you could generate a series of plots over the top of each other to see how mass is affecting this system. At the moment though, there's still some user input required to do that. You still need to, every single time you want to change the mass, open up this block here and type in the new mass, which is obviously not ideal. So let's now talk about deriving the simulation settings from MATLAB, as well as exporting data out from the simulation. Turns out that MATLAB and Simulink are designed for this functionality. It makes it really easy. All we have to do is specify, instead of hard-coded numbers in our Simulink model, we specify variables, and then we define those variables within MATLAB, and then Simulink will be quite happy to use the variables stored in the workspace within the simulation. So for example, instead of calling this 10, let's call it U1. Instead of calling this 1 on 6, let's call it 1 on M. And you'll see when you type these things, it tries to use things that are already in the memory, like MATLAB built-in functions. We don't want to do that. We want to use a variable called M. This is okay, this is okay. This gain here was going to be minus B. So minus B. This gain here was minus 1 on C. 1 on C. And you'll notice that these blocks now are red because Simulink is telling you that you're using variables that don't yet exist, which makes perfect sense. We haven't defined them in a script anywhere. Why would Simulink know what C or U or B is? This is okay. We'll leave them like this until we go and define those variables. Perhaps I also want to parameterize the initial conditions. So I will imagine that I'm going to have a vector called Z0 that's going to store my initial conditions. And if that's the case, then that vector's first element is going to be the initial conditions for this state. And that vector's second element is going to be the initial condition for this state. And again, it's gone red because that vector doesn't exist yet. Okay, knowing what parameters we need, let's go and define those within MATLAB. I could do this from the command window. That'd be fine. Instead, what we're going to do is do it using a script, because odds are we're going to want to run this more than once. So we'll create a new script, and let's call this script sim control or something. So this is the script which is going to define our parameters and run the simulation. Okay, so what do we need to do? We need to do three essential tasks, right? We need to define our simulation parameters. Then we need to somehow run the simulation, preferably not manually by going back and having to click the green button. And then we need to analyze the results. To define the parameters, we just need to have those things exist in the workspace. So we could do that within the script. We could say b equals 1, for example. And if you do that, that's fine. Simulink will then be able to see that variable as soon as the script is run, and it will be able to use that in its analysis. What we would probably prefer to do is to have one function which defines all of the parameters, so that if we'd like, we could have a whole bunch of these set up for a whole bunch of different conditions and have that function run all over again. So I'm going to create a function which will return all of the parameters we need. We needed a B, a C, we needed an M for mass, we needed to know Z0 as well. And I think that's everything, right? We can double check by looking back at our Simulink model. B, C, mass, Z0 fills out these two. And the input, of course. So those things are going to be returned. They're going to be the outputs of a function we will create that's going to be called something like setupSim. Maybe we'll call it model parameters. Basically, we're creating a function which is going to set up the simulation. And that function shouldn't take any inputs. It's just going to produce some outputs. That function doesn't exist yet. We're going to have to create it. So let's do that. I'll have a new empty mat file. And inside of that mat file, I'm going to write function output equals function name inputs. So this is kind of my default function header syntax, and I change these things based on what I'd like to happen. So I've already dictated the order of the outputs here in the way I'd like to call it. So I'll just copy and paste that here. So now it's going to output B, C, M, Z0, and U1. And I've decided I'm going to call the function setupSim, so I'll copy and paste that over here as well. And finally, this function doesn't take any inputs, so I'm just going to leave it like that. And now within this function, I'm going to define the parameters which drive the simulation. So I need a B, I need a C, I need an M, I need a U1, and I need a vector Z0. Okay, let's do, just to start with, B equals 1, C equals 1, M equals 1, U1 equals 1, and Z0 will start at 0, 0. So you could, remember, I'll just click save, Control S, and then save it as setupSim. It's important to save it with the same name you've given it here. I could have defined all of these within the main script. That would have been fine. But usually writing these as functions, making this modular, makes for an easier experience. All right, I'm done modifying that function. So now if I run this script and it gets up to this point, it's going to define all of those parameters. Next, what we need to do is automate the process of clicking this green button and running our Simulink simulation. And we do that using the sim command in MATLAB. So if we just go sim and we give it the name of the Simulink model it needs to sim, which is myFirstModel.slx, myFirstModel.slx, then MATLAB will go away and run the Simulink model myFirstModel.slx. This is the equivalent of pressing the green button. If we do that, it's going to produce something in the workspace, just like before, called out, which contains the simulation results. If you don't want it to be called out, if you'd like it to be called something else, you can do that. You can call it, for example, results. And now it will store the results of that simulation in a structure called results. Okay. Finally, what we would like to do is analyze the results, but at this stage it's prudent to check that we've done everything else right. I like to, at the top of my scripts, before I run anything, add a clear vars and a close all and a CLC. And what this does is it removes any variables that are already in the workspace, closes any figure windows that might be open, and then clears the command window as well. So I know that I'm starting from a fresh slate. I can't have the results of a previous simulation or the parameters from a previous simulation impacting what's happening now. And now I'll run this script. When I run this script, it's cleared everything in the workspace. Then it's defined these variables. Then it's gone away and run myFirstModel.slx using these variables and stored the results in a structure called results. And if we look what's inside of results, just like there was in out, we now have t, z1, and z2. And we can plot those things. If I plot results.t against results.z1, I'm going to get, in this case, a system which settles because of the parameters that we've chosen. Cool. We have one final thing we'd like to do, and that is to automate this plotting process. I'd rather not have to plot these things manually every single time. I'd like my script to do it. And again, the way we achieve that is using functions. I would like some function which doesn't produce an output, it just creates a plot. And the syntax in MATLAB for a function which doesn't produce an output looks like that, if you'd like. Or you can just call the function name without assigning it to an output. So I'd like a function which doesn't produce an output, takes the results structure as an input, and plots those things maybe on a subplot. So let's see, let's do, I'll call my function plot results. I'll call my function plot results, and it's going to take in results, which is the output of the simulation, as an input. Okay, plot results doesn't exist yet. I have to create it. So we'll create a new function. And same as always, outputs function outputs equals function name of inputs and end. In this case, I don't want any outputs. And function name, well, I've already said the function name is going to be plot results. And it's going to take a structure called results as input. Okay, MATLAB's throwing up a big warning now saying that I'm not actually using that input, but we're about to. So I would like to plot both of my states against time. So I'm going to need some sort of figure window. I'll do figure 1 so that every time I run this, it overwrites figure 1 instead of creating a new figure every single time if I just use the figure command. And I'd like to do this using a subplot because I have two things to plot and I don't want two separate windows to plot them. So if I use the subplot syntax, subplot 1, 2, 1, that says I would like 1 row and 2 columns worth of subplots, and the one I'm talking about presently is the first one, the one on the left. Then after that, I'd like a subplot 1, 2, 2, which says I would like 1 row and 2 columns worth of subplots, and I want to talk about the second one. In the first one, I want to plot results.t, the time vector, against results.z1, the first state. And in the second subplot, I would like to plot results.t against results.z2, the second state. It's prudent to put labels on these things. So let's go X label time t in seconds, Y label state Z1, which was position, which is measured in meters. And we need some labels for the second state as well, which is momentum. Time t in seconds, state Z2, which is momentum P of t, measured in kilogram meters per second. We now need to save our function, plot results, again with the same name as what we've called it here. And once we've done that, we should be good to just run this script. And now, when we run this script, it should clear all the variables in the workspace, close all of the open windows, clear the command window of output, define these parameters, run the simulation, store the results of the simulation in a structure called results, pass that structure into a function called plot results, which will then plot them on a subplot in figure number 1. Let's see how we go. And here it is, figure number 1. So in this particular instance, over 100 seconds, all the transient behavior seems to be done by 20 seconds or so. It's hard to predict how long it's going to take. So I'd probably like to actually parameterize the simulation time as well, amongst the other variables I have control over. I can do that by opening up my Simulink model. And instead of simulating for 100 seconds all of the time, I'm going to simulate for a variable number of seconds. We'll call it t final. And so now my simulation is going to simulate from 0 seconds up to t final seconds. And it does mean I need to define t final somewhere. I need to tell MATLAB and Simulink what t final is. So what I'm going to do is add that to my setup sim function. It's now going to return t final as well. I need to modify the function itself. U1 and T final, and I'll make that one of the things I can control. Let's make it, let's start with like 30 seconds. Okay, I'll run the simulation again now. And you'll see the results of the simulation and uploaded with a bit more resolution. We can actually see what's going on because we've only simulated for 30 seconds instead of simulating for 100 seconds. And actually similar things are done even sooner, so I can change this to something like 17. And if I click run on the script, then we can see the things with a bit more resolution again. All right, that should be all the information you require to complete Lab 2. I hope this helps.